Hi everybody, welcome back to another video. In the last video, or in the last section, we talked about what happens when we take 2 points and we move 1 point closer to the other and basically turn them into 1 point, so we could be talking about a tangent line instead of a secant line. And I used this term in the last video. It's something you may have heard of before or seen in a past class, but we're going to be talking in this video about something called a limit. And so the idea of a limit says what happens if you get really, really close to something. So we're going to be talking about kind of the idea of a limit and what is a limit and what does it mean for us. And then we'll kind of get into in the next few videos about kind of why do we need that, and we'll get into kind of the idea of a formal definition. So it's always good whenever you're talking about something new to have kind of a formal definition of something and an informal definition. We're going to look at the informal definition first. So to get started, here's a little bit of new notation for you. And this is the notation that we're going to use every time when we're talking about a limit. It says that the limit as x goes to some number, we're going to call that number a, and the question is that we want to look at is what is happening to f of x. So when you see something like the limit as x goes to a of f of x, that's how this is read. So you can read this as the limit as x goes to a, or as x approaches a, of f of x. And the way to think about this, and it's probably going to be equal to something, for now we'll just say equals L. The idea of kind of what this is saying here, it says that as x is getting really, really close to some number that we know about, what is happening to f of x? What is f of x getting really, really close to? Here's kind of another way to think about this. It says that as x gets close to a, what does f of x get close to? And in this case, we're just calling that number L. So if you want to use these arrow notations to talk about getting close to or approaching a specific value, you could say x gets close to a, f of x gets close to L. And let's look at an example, kind of what this looks like. I'm going to give you a specific function here. And so let's say something like f of x equals x squared minus x plus 2. And I could say something like, well, what is the limit of this function, well, of f of x, as x approaches 2? So what's happening to f of x as x is getting close to 2? Well, if you were to graph this, let's see, this is a quadratic that opens up. It looks something like this, and you could say, well, let's see, some kind of quadratic. And the question is, as x is getting really close to 2, so let's say you're kind of moving really, really close to x equals 2, and you're kind of looking at a small window. This is essentially what a limit is going to be doing, is it's going to say kind of pick a small window around a point on the graph where x is equal to 2. What is the y value? What's kind of a small window around the y value? And we'll look at that more in depth in a couple of sections, but what is y getting really, really, really close to? And in this case, y is actually getting really, really close to 4. And one way to test this, and we'll see this again a little bit later, is that if you were to just plug in 2, you get 2 squared is 4, minus 2 plus 2, you actually just get 4. So as x gets close to 2, y is getting close to 4, and so this value up here, your output there would be 4. Okay, so the idea here is what is y getting really, really close to as x approaches a specific number? Let's take examples really quickly and just kind of see what this looks like. So here's one that's a little bit more complicated, not too bad, but x minus 1 divided by x squared minus 1. And we could ask something like, what is the limit as x approaches 1 of x minus 1 over x squared minus 1. Or in other words, the limit as x goes to 1 of f of x. You could just write f of x, or you could just write whatever your function actually is there. That's fine. And so the question is, what is this equal to? What is the L that was on the other side? Okay, now this one's a little bit trickier because when we talked about the last example, I mentioned the word domain. And so if you think about the domain of this function, the domain is all real numbers except you're not allowed to use 1 or -1, okay? If you use 1 or -1 as your x value, then you're dividing by 0 on the bottom, and that's not allowed. So we could write out here that the domain is all real numbers except x equals 1 or -1. So I'll tell you what, I'll just put plus or minus 1, okay? And so what I hope that you see here, we can still talk about this limit. And so when we talk about the limit of a function, that's actually a different question than saying what's the domain. In this problem, x equals 1 is actually not even in the domain. You're not even allowed to plug in 1, but we can still look at the limit as x goes to 1 over here, even though 1 is not in the domain. So this is a really important distinction at the beginning here. Don't get this confused. Don't get a limit confused with asking what's the domain. Those are two different questions, okay? So how would you approach this problem if you can't actually plug in 1? Because in the earlier problem, we could plug in 2 and there were no problems there. And so what you may remember from the last video is that we talked about kind of getting really, really close. And you might remember that one of our points was x had an x value of x equals 1, and another point had the x value of 1.1, and then 1.01, and then 1.0001, and we got just really close to 1. So here's a question. What happens to f of x if you plug in a value of x that's really close to 1, not equal to 1 because that's not allowed, but what about really close to 1? So for example, what if you found f of 1.01? And then could you find f of 1.00? I guess I threw 3 zeros in there. Let's say f of, we'll use all of them, I guess, f of 1.001. What about f of 1.0001? What about f of 1.000, let's see, 4 zeros in there, 1? Okay, you kind of get the idea here. You could kind of keep going with this and say, well, what happens if you plug in values that are getting closer and closer and closer and closer and closer to 1? The idea is as x gets closer and closer and closer to 1, what is your output getting really close to? What are you finding here for your f of x values when you plug in x values that are getting really, really close? So I tell you what, go ahead and take a second, pause the video, and go find f of 1.01, f of 1.001, and all these other ones, using the function value that we have from the beginning. Okay, did you do it? So when I plugged in f of 1.01, I got something like 0.497512, and I'll just carry this decimal pretty far just so you get the idea that the further the decimal is in general, it's going to be good for you to kind of take that decimal really far, just because we're going to compare decimal places that are not just the tenths and hundredths place, but that are pretty far down the line. So don't chop off that decimal, otherwise things are always going to look the same. We want to carry that pretty far when we're talking about a lot of fine detail, which we are here. So for 1.001, I got something like 0.4975012. I guess you don't have to go 15 decimal places, but more than 2 or 3. How about like 7 or 8 is fine. The next one, 1.0001 with 3 zeros there. I got something like 0.49997500125. And the last one here, or the last one that I chose, because we could have kept going, is I found something like 0.4, oh boy, 999975. I'll just stop there because then there's like 3 zeros after that. And so hopefully you kind of get the idea here. What is f of x getting really close to as you kind of get closer and closer and closer to 1 with your x values? Well, hopefully that should be pretty clear that the limit of this thing is actually going to be, so I would say the limit as x approaches 1 of f of x sure seems like we're getting 0.5. It's going to, if we go further and further and further, and x gets closer and closer to 1, we're going to get something like 0.499999999, and many nines there, and so we're going to just basically get closer and closer and closer and closer to 0.5. Now, what we'll see in a second is that we shouldn't just look at values of x that are getting closer to 1 that are bigger than 1, right? These all look like 1 point something. We really also should check on the other side as well. So let's say we have here with f of x equals x minus 1 over x squared minus 1. We shouldn't just check 1.000 something. We should also check, what about f of 0.99 on the other side, and say, like on the other side of 1. So these are decimal values that are actually also getting closer to 1, but they're all numbers that are less than 1. Okay, so f of 0.9999, we could keep on trying, keep on getting further, and hopefully get the idea here. Kind of the more nines you throw in, the closer you're getting to 1, but still always on that lower side. And so, in other words, on a number line, if 1 is right here, you want to check from numbers that are going from the right, meaning getting closer and closer to 1, but that are bigger than 1, and numbers that are closer to 1 that are less than 1, and kind of check from both sides. And we'll see why in a second. But hopefully when you test this, you should also get numbers that are getting really close to 0.5. Okay. If not, we'll see what happens in just a minute. But go ahead and take a second, and you can find all 4 of these and test these as well. And if you do all these, you should get something like, I got 0.5025, 1, 2, 5, 6, keep on going. The next one, I got something like 0.50025, and there's a little more after that. The next one, 0.500025000125. Okay, the next one, 0.5. And really, this should feel repetitive. It should feel tedious at this point. And all that we're doing here, all that we're verifying, is that the limit as x goes to 1 of this function, even though 1 was not in the domain of this function, we can still find the limit of this thing is equal to 0.5. Okay, so we can kind of, generally we can find limits by kind of plugging in values closer and closer and closer to that specific value that we're talking about. So here's one for you to practice with. This is a weirder function. I told you that not all of our functions are going to be kind of nice and easy ones that you've seen before. This one is probably one that you haven't seen. It's going to look like this. F of x is equal to the sine of x divided by x. Okay, and what we could look at, what gets kind of interesting here, is if we look at the limit as x goes to 0 of this function. And this is actually going to show up again down the road as one of our kind of interesting examples when we look at some trig functions. But if we look at the limit as x goes to 0, you should ask a question like, is 0 in the domain? Remember the first problem we saw, we could plug in 2, and 2 was in the domain. There were really no issues there. So is 0 in the domain here? And so hopefully pretty obviously the answer is no. And so what we can think about then is what happens if you take values of x that are getting really close to 0 and plug those values in. So what happens if you find f of 0.01 and f of 0.001? Okay, now I said don't just try values that are bigger than that value of a, which a in this case is 0. Also try to look at what happens when you have values that are less than. So how about negative 0.01 or f of negative 0.001? These are also getting really close to 0. And you could do, 5 in either direction like we did last time. At some point it gets a little bit tedious here, and so what we're going to see is that this is not necessarily the most efficient way, but it does help us get at the kind of intuitive definition of what is a limit and how does that behave. Okay, so what ends up being pretty interesting is if you test these values and plug in something close to 0, both in the positive direction and in the negative direction, what you actually end up getting is 1. which is not at all intuitive. That's a little bit weird. And so that ends up being our limit, but it's not at all obvious. So you can test that by plugging in some values in either direction. But just kind of an interesting example to think about, as we probably haven't seen an example like this before.